Hi, I'm Marshall Bloom, one of the organizers of the conference and the moderator for this morning's first plenary session, H5N1 1 year later. Just about a year ago at the 10th annual ASM BioDefense and Emerging Diseases meeting that we hosted an early morning session on H5N1 and the controversy which at that time was just about beginning to take shape. And a year after that, amazingly, the topic has stayed in the forefront not only of the scientific and the scientific publishing world, but even in the public's eye and the politicians' eyes. And so Gene Patterson and I, Gene's the other organizer of this conference, decided it would be extremely timely to have another session on this topic with a completely new set of speakers to sort of fill us in on what's happening, what the major, a little history, timeline, some actual science, and then sort of what the implications and what people have learned from this. And so that's what we're going to try to do this morning. We have 6 speakers, all on very, very different topics, although I'm sure there'll be a little bit of overlap. What we're going to do is we're going to let each one of the speakers give their talk. They're going to sit down in the audience so they can see the slides of their co-presenters. And then at the end of that, so we're going to ask you to hold your questions until the very end. Then we'll bring everybody up on stage and we'll have questions and answers for the remaining time in the session. So with that, I'd like to introduce this morning's first speaker, Arturo Casadevall from Einstein, and he's going to give us sort of a general overview of the controversy and the issue. And Arturo, you got the... No, I don't have it. So who's got the slide advancer? It's right here. I didn't take it, but it's right there.
Thank you, Dr. Bloom, and thank you, Dr. Patterson, for inviting me. I think that we have to get back. Okay, so my job was to give an overview of the H5N1 controversy, and as you hear, I think that you're going to hear some of the same things repeated over again, but I think that's good. Everyone will say it is slightly different. I'll begin by saying that I serve on the National Science Advisory Board on Biosecurity, that I am speaking as a private citizen, and that none of my words should be taken as representing the views of the NSABB or that of the United States government positions. So with that, I think let's think of this controversy. This controversy begins in the fall of 2011 when 2 manuscripts reporting gain-of-function experiments for H1 showing that you can confer upon it mammalian transmissibility are reviewed by the NSABB. In December of 2011, the NSABB unanimously recommended redaction of mutational data informing on amino acid residues that confer capacity for mammalian transmission. In January of 2012, the community began a voluntary cessation of gain-of-function experiments. In March 2012, the NSABB reconvened. There was an intervening WHO meeting at that time, which had also recommended a publication. And they were informed that redaction was not an option given the available legal framework in the United States. And then the committee voted unanimously for publication of the Kawaka manuscript and voted 12-6 in favor of publishing the Fushier manuscripts, both in revised form. Now, in May, June, both papers appear in revised form. I stressed that the NSABB voted on a revised manuscript and not necessarily in the original manuscript. And one thing that remains not in the public record are the original manuscripts. And I think that at some point, either the authors or the journals ought to find some way to get that, because that's part of the history of this whole time. So in the second half of 2012, the controversy continues. On June 2012, the voluntary moratorium remains in place. In August 2012, the U.S. government announced continued supporting for the moratorium, gain-of-function experiments, while a new framework is developed. In December 2012, there was a meeting at the NIH to discuss all aspects of this controversy. in this February, we now have a framework about going forward for research in the highly pathogenic H5N1 viruses. The bottom line is the gain-of-function experiments can resume with more oversight, and these are the criteria. This was taken from a paper in Science last week. I'm not going to read them all, but you can even see in them that there are some aspects of controversy. For example, you look at first, such a virus could be produced through a natural evolutionary process, raising the question, what is a natural evolutionary process? I would not be too hard on any of these things. You have to realize that the scientific community is trying to work its way through something that is very difficult. There is no precedent for any of this. So even though as these guidelines emerge, they tend to be discussed, they tend to be modified, things may not happen as fast as you want, but I have a lot of confidence that we are working through the process. However, I would argue that the genesis of this controversy began a decade earlier. As you know, the world changed in 2001 with mailings of Bacillus and traces spores in the mail. The country discovered that 6 envelopes could cause tremendous disruption, or houses of government were emptied from the first time since the War of 1812. However, there have been previous papers in the literature that had raised eyebrows. There had been the Ectromelia paper in 2001 showing that the insertion of IL-4 could potentially defeat vaccine immunity. There had been a paper showing that the variola virus could complement regulatory proteins, could allow it to become pathogenic, and there was a very controversial paper in 2005 analyzing the points where the milk supply would be vulnerable to the introduction of botulinum toxin. So the government responded. We had new laws. We had a series of biosecurity initiatives, including the establishment of the NSABB, and we had the creation of lists, which continue to be modified. In 2003, the NRC issued a report on dual-use research. This identified 7 experiments of concern that became the basis of a subsequent report by the NSABB. In 2005, the NSABB was created to recommend strategies for efficient and effective oversight of federal-funded and conducted dual-use biological research. The goal was to consider both the national security concerns and the needs of the research community. It is important that this body advises the government. It does not advise journals, universities, or institutions. And problems brought to it have to be brought in through the venue of the federal government. In 2007, after 2 years of a lot of work, it issued this document that I think is going to become very important as time goes on. I will point out to you that when we first got together in 2005, we didn't think we could do it. We simply couldn't imagine coming up with definitions that work or creating an area that would be outside, for example, would exclude cancer research and things like that. We did not want to interfere with the ongoing science, but after a lot of discussion, it was possible to create a narrower type of definition. And I'm not going to read it, but this is all in the public domain. There were 7 categories of concern. These are broader than the original FIN criteria. Enhance the harmful consequences of biological agent or toxin, disrupt immunity, confer new properties. You have 2 in red here. These are 2 that we thought that apply to the 2 papers with the gain of function, increasing the stability, transmissibility, or the ability to disseminate a biological agent or toxin, and certainly altering the host range from birds to include mammals. So I'm going to give you some personal impressions on the H5N1 controversy. I would tell you the NSABB was not sure what even though they came up with this document, and even though this document took a tremendous amount of work, we were not sure what a dual-use paper was until they considered the 2 H5N1 gain-of-function papers. This was one of those moments in which you realize very clearly where the boundary may be. The initial concerns were about biosecurity, but as 2012 progressed, concerns about biosafety and biocontainment became more prominent. And in recent discussions, in recent meetings, the discussion has shifted more from a the worry about a malevolent actor using them to the fact that these things could get out of the lab and cause a pandemic in themselves. I think the biosecurity concerns are still there, but there has been a shift in concern as the year went on. Reasonable and intelligent scientists found themselves in disagreement as the issues forced judgment calls without data. This was a real people that understood the issues basically had to make a judgment call. And I think that one of the most important things is that these were all well-intentioned calls, whether you were on one side of the debate or the other, and that people were navigating through problems that they had never, in fact, faced before. We didn't have to make decisions like this in science. And I think that no matter what happens and no matter where you are in the debate, that the important thing is to always maintain respect for the other side. Facts became major points of contention. For example, the H5N1 case fatality ratio became an issue for debate. So what you found is that as you didn't have the facts to really make a judgment call, you needed that the items that were going into it became major points of debate. Science is different from religion in that we have a mechanism for conflict resolution. You can do an experiment. In other aspects of human conflict, basically, there is really no mechanism for resolving. You almost have to live and let live. However, here we were in a situation in which decisions were needed, and there was no time to obtain the necessary data to forge a consensus. Scientists consider steps that had no precedent in ordinary science. Redaction of manuscripts. I mean, this is something that had never really been recommended or thought before, to take out data from them. A moratorium on powerful experimental approaches, such as gain-of-function experiments. I feel that a cogent case for gain-of-function experiments remains to be made, a scientific rationale why this needs to be done. And I have brought up the issue as to whether the same information can be obtained by other means. Now, the reflex is always no, it cannot be done, but I will give you two examples that will give you something to think about. If you were sitting on the moon and you were watching Earthrise, and you had this blue ball coming up in the sky, and you had all the instruments that we have to take today, could you work out much of the chemistry of the life cycle? The answer is yes, without doing a single experiment. But it would require a very, very different approach to the problem. Perhaps even more telling is what is going on in cosmology today. We are in the midst of a great revolution in cosmology where astronomers and physicists can understand almost everything that has happened in the universe and where it's going. I posit to you that they can do no experiments. All they can do is measure, observe, and think. Astronomers cannot knock out a galaxy and see whether the other ones twinkle, or give anything in the heavens gain of function, and yet this is a field that is thriving. So some of the challenge that I've thrown to the field and what I'd like to see developed is a cogent rationale for doing this kind of work that is not just, well, we can do it and it gives us important information. The biological scientific community has been sensitized now to the dual use issues. This is something that did not exist a year and a half ago. I give you an example. This is a paper that just appeared in JID, in which a gain of function experiments, and there are two things in it. One of them is a commentary that was co-authored by Dr. Moran, and also an editorial explaining why the work is important and why it should have been done and why they're publishing it. This is a different environment that we were operating a year and a half ago. In the past year, I'm the editor-in-chief of MBio, and I'm very interested in history, and I know that history, we were living in a historical moment, and one of the things that I have tried to do has been to commission many of the views, to put them in writing, because in the future, people will look back at this time and try to understand it based on what people were thinking at the time. And I'm happy to say that we have at least 10 or 12 essays by many of the major players in the field dealing with, for example, comparing the H5N1 affair to Asilomar to some of the major things that we're facing, from biocontainment to whether these experiments should be done. So the situation today, 1.5 years later, I believe the controversy continues. We're sitting in a room in which there is a standing room at the back. There are a couple of chairs in the front. This is not going to go away. However, we need to admit that gain-of-function experiments have been critical in establishing the potential of H5N1 to acquire mammalian transmissibility. No matter what you say, we did not know this before. You could have argued that perhaps this virus did not have the biological capacity to do it. Well, it does. So now H5N1 remains an existential threat to humanity. I think that if you watch the movie Contagion, which Ian Lipkin will tell you much more today, I think you can see what would happen to society even with an epidemic that had a fraction of the maximum mortality that could be associated with this. Certainly, those of us who lived through Sandy, Katrina, and all the can see how our society is so complicated that it's become very vulnerable to any sort of disruption. And any pandemic or any, as we saw with SARS, will be devastating to our way of life. I would argue that the influenza research establishment remains humanity's best defense against the calamity of a new pandemic. So we now have new regulations in place to reduce biosecurity and biosafety concerns, but I ask, what would happen to this field? Will the best and the brightest go into this field? Would you take a research project where your paper may be held up? And I think we need to really think through this, because if H5N1 remains such a threat, and if the research community is the best defense on it, we need to make sure that as we work through this controversy, that we don't interfere with humanity's best defense. And with that, I'll end, and perhaps the next speaker can come.
Thanks, Artur, for that cogent and salient commentary. As for those of you who came in a little bit late, there are still a couple of seats down here in front if you'd like to sit down. And we decided that we're going to hold the questions until the end. So with that, I'd like to introduce this morning's next speaker, Jeff Taubenberg from the Division of Intramural Research at the National Institute of Allergy and Infectious Diseases, who's going to talk about some of his experiences and their relevance. Jeff?
Thanks, Marshall. Thanks for the invitation. Good morning. I thank Arturo for the very nice introduction to this topic. I was asked to talk about the dual-use implications of research on influenza viruses, and after much thought about this, I've decided actually to not exactly talk about what my assignment was, but I am going to talk about dual-use implications of influenza virus biology. And so the one thing that I'm basically not going to be doing is talking about H5N1, but I'm going to be talking about influenza more generally, to cite some examples of what influenza viruses are doing in nature and how that relates to this ongoing controversy. So very briefly introduce you to the protagonist or antagonist of this story, which are the influenza viruses themselves. Just a couple of points. I will be citing some examples that deal with the kind of molecular virologic aspects of viruses, but it's not necessary that we think about the details, but just a couple things so that we're all on the same page. The viruses that are at the heart of this controversy are influenza A viruses, which are single-stranded RNA viruses with a segmented genome. They're just two features of their biology which I would like you to keep in mind. One is that, as typical of RNA viruses, they have an error-ridden polymerase complex. Their RNA-dependent RNA polymerase has a high error rate, and so these viruses can evolve and adapt very quickly under various kinds of both positive and negative selection pressures. Secondly, because it has a segmented genome, if one host, and specifically one cell in that host, is co-infected with two or more different parental influenza viruses, you can mix and match these gene segments to create viruses, so-called reassortant viruses, containing one or more genes from each of the parental viruses, and that these new genotypes can have very different and unpredictable phenotypes. These two things are essential to understanding how influenza viruses do what they do in nature. The next thing that's very important to understand is that the host range of influenza viruses is extraordinarily diverse. It's thought that the natural reservoir of influenza viruses are wild birds of probably hundreds of species in multiple orders. So it's not just one particular species. So we think of ducks, for example, and other anseriform birds. But these viruses are really in a huge number of species, and I know Vincent will be talking about this later. But that the important feature that I want to make on this slide is that influenza viruses have the ability to move around between different host species, not to just cause one-off zoonotic infections of one host to another, but to actually stably adapt from one influenza from one host to another, so that avian viruses in wild birds can adapt to domestic avian species like chickens and turkeys. They can also adapt to mammals, both wild mammals as well, very divergent wild mammals, but also to mammals of grave importance to us economically and agriculturally, including pigs, horses, dogs. But then most important for us in the room is that influenza viruses have the ability to adapt to humans, which they readily do. You'll notice these arrows kind of go in a bunch of different directions because flu viruses have this great potential to move around, and this is one of the major problems in the control of influenza viruses. So this leads us to what I would call the sort of circle of the influenza problem. And I know the text is a little small, so the points that underlie what I would call the influenza problem are that influenza viruses are extremely diverse antigenically and genetically. They evolve very rapidly. New strains continually emerge by these processes of mutation and reassortment, and their host range is incredibly extensive. That is, many hundreds and hundreds of species, both avian and mammalian. Influenza viruses continually and continuously continue to cause disease in domestic animals like chickens, turkeys, horses, pigs, dogs, etc. They are a cause of major epidemics, and I know that there's a lot of concern about a new pandemic might be caused by H5N1, but it's important to remember that seasonal or annual influenza viruses in humans is a major cause of morbidity and mortality, and that many tens of thousands of people can die in the United States every year, up to 40,000 or so, of seasonal viruses, and that the impact of seasonal infections in humans can often actually be greater than the impact of pandemics, at least in the first year of a pandemic. And then the last feature is that pandemics themselves appear occasionally sporadically in humans. We are not able to predict the emergence of pandemics, but that pandemics themselves, while novel viruses that are ultimately derived from an animal source and adapt to humans, their epidemiologic characteristics are also quite variable. Some are more severe than others. So, thinking about this and this topic, influenza viruses and dual use, Arturo talked about what the dual use criteria are, and again, I'm not going to read this all either, but just to make a couple of words. So, research that's directly misapplied to pose a significant threat with broad potential consequences to public health and safety, plants, animals, humans, and national security. So, I thought that maybe we could think about rephrasing this sentence in the context of what influenza viruses are doing in nature. And so I would like to posit this as the basis for the rest of my talk, which is that because influenza viruses in nature have a significant threat with broad potential consequences to public health, safety, animals, and national security, it's crucial to study them. And that influenza viruses in nature regularly undergo things which fall under this rubric of dual use concern, that they undergo host switch events, change their tropism, change their pathogenicity, etc. So if we go through these criteria that were also previously listed in the last talk, enhance harmful consequences, disrupt immunization, confer resistance, increased transmissibility, alter host range, etc. Let's think about this from the context of what influenza viruses are doing. So I think that we make the point that I think that influenza virus is a chief threat, that it's very important to think about the national security aspects of this work, the biosafety, biosecurity, and the regulatory framework under which this work is done, but it is important to realize that influenza viruses in nature are doing things of import for us. So let's take some examples down this list. So enhance harmful consequences. So here's an example of how nature can break rule number one, which is enhance harmful consequences. Low pathogenicity avian viruses that cause little to no disease in their hosts can acquire mutations that allow them to become highly pathogenic avian influenza viruses that can kill 100% of infected poultry flocks. Here's an example not of H5 and all this concern of H5, but in the 12 or so years that H5N1 viruses of the Eurasian lineage have been circulating, there have been handfuls of other independently emerging highly pathogenic avian influenza virus outbreaks around the world, including in the Americas and in Europe. And in this case, I cite two examples of independent emerging high-path outbreaks that occurred in Canada in 2004 and 2007. Some of these were associated with human infections, including many cases of conjunctivitis. But without going through the molecular details, there's a class of mutation that viruses can obtain when they adapt to chickens that allow them to become highly pathogenic, which is an insertion mutation at the cleavage site of hemagglutinin. And here I've aligned just a little bit of the H7 hemagglutinin and shown an alignment with a couple of strains. Some of these two independently emerging viruses are the two outbreaks in 2004 and 2007, which have different sequences here. The 2007 was just not a reappearance of the 2004 virus. It was a new independently emerging virus. But in this case, this 2007 virus is almost completely identical to a low-path duck virus that was actually sequenced in my lab, provided me by my collaborator Dick Slemons, who does surveillance on wild birds regularly in different parts of the country. And so a virus that caused no disease in a mallard in Maryland in 2006 is basically identical, except for this mutation, to a virus that killed 100% of chickens in British Columbia 1 year later. So this is an example of how viruses in nature can change their harmful consequences. We don't have to go to bird viruses to think about this. We can just think about human influenza. And as I've mentioned, seasonal influenza viruses change their epidemiologic impact on a yearly basis in unpredictable ways, but some epidemic years are quite severe. And if you recall back about 10 years ago, there were H3N2 strains circulating in 2003 and 2004, Fujian-like viruses that caused very severe outbreak in epidemic in humans. And that the molecular details of what happened to these viruses as they emerged is not that important, although my lab spent some time looking at that. But there are both the reassortment and mutations that occurred that changed the phenotypic properties of these seasonal viruses to lead to this very big outbreak, including the large number of deaths of children of this in this Fujian year in 2003. So this is another example of influenza breaking rule number one. Let's think about breaking rule number two. Disrupt immunity and immunization. This is something, again, that influenza viruses are particularly good at. So the reason that the vaccine is reformulated, and Nancy Cox will talk about the WHO surveillance network, the effort to constantly keep up with this rapid evolution of influenza viruses in humans to reformulate the vaccine, is the fact that influenza viruses in nature are actually undergoing selective pressure to acquire mutations in their hemagglutinin that actually allow them to escape pre-existing immunity either from natural infection or immunization, which is why the strains for the immunization vaccine are changed every year to keep up with this rapid immunity. So this is an example of a nucleotide tree of H3 hemagglutinin showing how much change occurs, that you can actually date influenza viruses quite accurately from 1 year to the next because of this rapid evolution. And this rapid nucleotide evolution in the hemagglutinin gene leads to the phenotypic change of escape from pre-existing immunity. And the consequences of that are, this is the number of significant antigenic changes that have occurred in the H3 hemagglutinin since its emergence as a pandemic in 1968. And you can see that it's acquired an enormous number of changes. So each one of these bars is a significant antigenic drift that requires reformulation of the vaccine. This happens almost on a yearly basis. So let's think about breaking rule number three. Conferring resistance. Antiviral resistance to influenza is a growing clinical problem. There are 4 approved drugs for influenza viruses in 2 classes, the older adamantanes, the ion channel drugs, amantadine and romantadine, and the newer neuraminidase inhibitors, oseltamivir and zanamivir. And here I cite an example of a patient treated in one of our clinical protocols at the NIH. This was a person infected with an H3N2 virus a couple of years ago. And the person was treated with oseltamivir and was not getting better. And so in our surveillance effort, we actually isolate virus from nasal swabs every single day in a person as long as they're shedding virus and do deep sequencing. And in this case, what we had was a virus that acquired around somewhere between day 4 and day 6, acquired an in-frame 4 amino acid deletion near the active site of the neuraminidase. The consequences of this was that this particular virus with this novel mutation that hadn't been described before was shown in the laboratory to be resistant to oseltamivir, but also to zanamivir in a virus that was already resistant to both the adamantanes. So what you have is an H3N2 virus isolated from a human that is now resistant to all 4 available drugs to treat them. We have a pan-resistant virus. And unfortunately, in studies in ferrets, this virus does not appear to be attenuated. It caused as much disease and was fully transmissible ferret to ferret compared to the wild-type virus. So this virus could circulate in the community. And I think this is an example of how rapidly flu can break rule number 3. Increasing transmissibility, breaking rule number 4. The 2009 pandemic, as you probably know, was a reassortment event between 2 pre-existing swine influenza-adapted lineages. That both of these had caused occasional influenza infections in humans, that is zoonotic infections, but without any evidence of enhanced transmissibility person to person. But when these 2 viruses reassorted and exchanged gene segments to create the precursor of the 2009 pandemic, they acquired, this parental virus acquired the ability to spread efficiently person to person. Altering the host range, if you recall back the picture of the different host range of influenza, this is something that influenza viruses in the wild also do very well. And all pandemic viruses that we know about, that is from 2009, 1968, 57, and 1918, all have at least some genes derived from animal-adapted influenza viruses. So I think by definition, all pandemic viruses are emerging after a host range alteration in which a virus that's otherwise adapted to an animal adapts to human circulation. But it's not just human pandemics that are important for the altering of host range. This is something that's critical for the behavior of influenza viruses in general, and that you can find examples of these arrows going in every direction, and I could spend hours talking about different examples. I'll just cite a few. So wild bird viruses frequently adapt to poultry to cause high path flu. Avian viruses adapt to pigs, as example happened in 1979 in one of the parents of the 2009 pandemic. Equine H3N8 viruses have circulated for decades in horses, and yet 10 years ago, all of a sudden, underwent a host switch event where they adapted to dogs. And this is becoming a growing problem in veterinary medicine. Human viruses have adapted to pigs. H3N2 viruses have adapted. And back in 1918, the 1918 virus probably adapted to pigs during the pandemic itself to form the classical swine H1N1 lineage. Enhanced susceptibility of hosts. So most of you carry bacteria in your nasopharynx, like pneumococcus, staph, or other strep, that in general don't cause disease. But if you get an influenza infection, you can actually then, as a consequence of your influenza viral infection, get a secondary bacterial pneumonia, which is often a cause of significant morbidity and mortality. So I think this is an example of how influenza can enhance susceptibility of hosts, and that a very large percentage, almost 100% of fatalities in 1918 were associated with secondary bacterial pneumonias from these common pneumopathogens. Here you see examples of autopsies of both the 2009 pandemic and the 1918 pandemic showing these bacterial pneumonias with the kind of pneumopathogens that you would expect, pneumococcus, staph, group A strep, etc. Number 7, generate, reconstitute, and eradicated agent. I'm not going to talk about the reconstruction of the 1918 virus here, but what influenza viruses are doing in nature, which is that there is very good evidence based on serology and epidemiologic data that there is what has been called subtype recycling or antigen recycling, that pandemics of one era can actually come back with the same subtype in a later generation. And so in 2009, there was an example of this, that the older people in the population had immunoprotection against the 2009 virus, whereas the younger populations were susceptible and naive to this virus. And this was because the 2009 pandemic virus has an H1 hemagglutinin that's antigenically remarkably similar to that of the 1918 pandemic, the H1N1 virus of that era. And then so people who were exposed to the 1918 pandemic or the subsequently derived seasonal viruses in the first couple decades after 1918 had cross-protection against the 2009 virus. If you go backward, in the 1968 pandemic, there's serologic evidence that the elderly had some protection against an H3 pandemic that probably circulated in 1889 and before 1918. And if you go back to 1918 itself, you can find a similar evidence of immunoprotection of the elderly, probably from exposure to an H1 virus in the mid-19th century, possibly pandemics that occurred in the 1830s. So we have evidence of, in nature, the recycling of antigenic subtypes in pandemics, and so I think that you can say that influenza viruses are breaking rule number 7. There have probably been 15 pandemics in the last 500 years since 1510, if you will cast your mind back. And if you look at the pace of these pandemics, it's possible that pandemics are increasing in their frequency, although this might be relating to reporting. But all of these are examples of things that have occurred probably because of growth of human populations, changes in agricultural practices, the interactions of humans and domestic animals, the pressures placed on wild birds, but that the point being that all of these relating to the emergence of pandemics are occurring in nature using natural processes. So I think that we have critical needs. We need to understand the processes by which influenza viruses can do these things, by which they can switch from avian viruses to mammalian viruses and ultimately to human viruses, how they change their phenotypic properties. I think this is very important to be studied in a very careful way under the appropriate safety and regulatory framework that has been provided. So I think just in closing, I just want to say that I think that provide a little vignette, that as we focus on the dual-use implications of this work, I think that it's important to not lose focus about what's happening in nature. So like this peregrine falcon is focusing specifically on this pigeon that it wants to have for breakfast, it needs to be aware of the environment around it. And this is an example where it was not. And actually, I took these pictures. This was on the day the world was supposed to end on 12/21 last year, where it didn't end, but it did end for this falcon and this pigeon, because they both flew into this window here and both fell dead on the stairway below. This is the smudge on the window of the falcon. So I think that they did not have either West Nile or H5, but they were not paying attention to all the things that they need to pay attention to. So in summary, influenza viruses are extremely important human and animal pathogens, and their continuous and unpredictable evolution makes them such important pathogens, and that's why it's so important to study them, and that's why I think it's worthwhile thinking about how these viruses behave in the context of our discussion this morning. Thank you.
Thanks, Jeff. That was really, really informative and provocative. I'm absolutely astonished that we're moving ahead of schedule. I guess Gene and I must have been way too draconian in our instructions to the speaker, but I think this will be wonderful because it'll give us a lot of time for questions after all the talks are over. One of the components in the whole controversy that ended up really sort of on the front line about a year ago were the publishers, Nature and AAAS, of these two papers. And we felt it was extremely important this year to have a speaker who represented one of those two periodicals. So I'm very delighted that Barbara Jasny from AAAS Science Magazine was able to be with us and is going to tell us a little bit about the journal's perspective and with some maybe broader overview of what it meant for publishing at large and what it will continue to mean. So with that, let me introduce Barbara Jasny from AAAS.
Good morning, and thank you very much for inviting me. For the journals, the past year was really a roller coaster. And we were in a position to see some of the shortcomings of the system. The problems very clearly began before the publications were ready. And the problems arose in not recognizing the dual-use issues early enough and what the ramifications would be. As Tony Fauci said, the dual-use aspects didn't hit the radar screen of the scientists who reviewed the proposals for NIAID, in part because similar types of research looking at alteration of transmissibility have been going on forever. University biosafety committees in the United States and in the Netherlands also green-lighted the work. One lesson on which there is total consensus is the following, that the time of publication is too late to begin to resolve dual-use research of concern issues. So I'm sorry to show you another timeline, but we need to start in the summer and fall of 2011, in the early stages. Manuscripts were received from each group at Science and at Nature, and I'll be talking about the history at Science magazine. By the end of September, our initial technical review had completed, and we had begun our own security review. However, even at the time of submission, there was a meeting in Malta that the authors presented their work at. Journals do not prohibit talking to one's colleagues. And Ron Fouché, who is the corresponding author of the Science paper, and he himself is from Erasmus Medical College in the Netherlands, but did the work under a subcontract through Mount Sinai and NIAID. He did talk at this meeting, not about the specific location of the mutations, but about the results. So even as the papers were going through the early stages of review, there were rumblings in the social media and in the press that something was happening. Now, one point that Fouché examined and had been raised by reviewers, and so he went into more depth about it, was about virulence. Although the concern in natural transmission was the airborne route, Fouché used a very sensitive, very precise method of inoculation specifically for the virulence studies, intratracheal. And this is not related to how animals or people are expected to acquire the virus naturally. Under conditions of intratracheal inoculation, ferrets did die. Although this was accurately stated in the paper, it was not stated as clearly as it might have been in that initial version, and that initial version was the version that the NSABB first looked at. It does, let me just say parenthetically, tell you what good editors can do because the paper improved during the process. But it did lead to a misconception early on that the virus was more lethal than it actually would be under in vivo conditions. So by the time the paper was published in Science, we made a point of stressing, and just look at the part that's in red. In the abstract itself, we said, none of the recipient ferrets died after airborne infection with the mutant H5N1 viruses. And we made sure that there could be no misinterpretation. But again, we learned lessons about transparency. For example, there has been an uncertainty, especially in the international arena, over what exactly the BSL-3 conditions mean in different laboratories in different countries. And we have decided that we will, in the future, ask authors to go into more details about what exactly their conditions were, going to the point of specifying what training, what monitoring, what other aspects of security are there. Another lesson we learned that only a transparent version that makes clear what was done should be the basis for decision-making. And this has led us to consider even having some exchanges and editing exercises with authors before the manuscripts go for peer review to make very sure that in controversial areas, everything is clearly stated from the start. During the review process, we decided to do our own biosecurity review because we gathered from comments from the editors, from reviewers, that there was good reason to be concerned here. And after 9/11, many journals instituted formal procedures if we felt there was a paper that had dual-use concerns. And there was disagreement among the experts. Two who we consulted felt the paper should be published in its current form. One was very concerned about public reactions and other ramifications. Somewhat later, NIH asked the NSABB to look into the situation as well. And in the course of the discussions, one of the problems was that it seemed to be a moving target. What were we really worrying about? Were we worrying about rogue governments? Were we worried about terrorist organizations? Well, there were a lot of discussions that really influenza would not make a good bioweapon, that if you had anyone with any expertise involved in this, they would know that the virus spreads indiscriminately, that it's not so easy to engineer, and it's not very stable. All right, then we began, but maybe the terrorists wouldn't be so smart. Maybe we'd have crazy doomsday individuals. Was that something to worry about? What about accidental release? What about do-it-yourself students working in their garages? it was very difficult for the journals to get information that would help us to do a risk-benefit analysis and to proceed in a responsible manner. Frequently, the politics obscured the scientific issues, and it was clear that NIH was caught by surprise to some extent by the actions of the NSABB. The international reactions were not foreseen completely. So it really was a moving target. The NSABB then recommended that the papers not be published in their full form, and this was a first in the history of publishing. Oh, I'm sorry, I left out the lesson from all of that, that we need clear rules, clear regulations, and experts who are willing to give us their unvarnished opinions, and that's an important point. Okay, let me also say, before I go on, that while this was happening, the press was getting very much involved in it. Here, I would have to say that there was more than enough fault to go around. Certainly, Ron Fouché, in his statements to the press, was at times imprudent, saying that this is probably one of the most dangerous viruses you can make, did not help the situation. The New York Times headline that this was an engineered doomsday did not help. Paul Kimes stated that I can't think of another pathogenic organism that is as scary as this one. Michael Osterholm said, and I heard this myself, it is the Lion King of infectious diseases. It was not a good atmosphere. And a major lesson is that responsible communication with the public from the very beginning is vital. Because once the public begins to lose trust in the process, then things are going to go downhill. Okay, so we go back to the timeline again. And by the end of November, we heard about the NSABB decision and their recommendation to publish a redacted form. Bruce Alberts is the editor-in-chief of Science Magazine, and he was head of the National Academies, and he did not want to do anything to undermine the NSABB. He was willing to consider redaction, to consider, as their press release said, just highlighting the novel outcome, but not including methodological or other details. And he was willing to do that, but he said he would only consider redaction if information omitted from the publication would be provided to those responsible scientists who requested it as part of their legitimate efforts to improve public health and safety. So who had a legitimate need to see this? Well, public health individuals doing surveillance, also researchers who needed to be protected, who maybe were working with a virus that was only 1 or 2 mutations away from this very dangerous form. The guidance given to journals for how to redact the papers was rather vague. The NSABB did not want to be seen as giving orders to the journals, and that was understandable. Science and Nature both attempted to construct a redacted version, which meant cutting from something like 9,000 words, not counting the supplemental material, to about 1,200 words, and not providing details of methods or where the mutations were. So this takes us to February of 2012, and there was a WHO technical meeting. And we brought the shortened papers to that meeting. And there was a consensus, as people began to look at those papers, that the redacted ones didn't represent science with a small s. It was more like an advertisement, a press release, a birth announcement. And as discussions went on, government representatives were talking to lawyers to see if, all right, let's say you did this redacted version, could you have controlled access? And there were a lot of obstacles. If the information wasn't going to be given out freely, it violated the International Pandemic Influenza Preparedness Agreement that was a fragile agreement that brought together developed and developing countries in an effort that was seen as for global public health and a global benefit. Realistically, how would you give information to some scientists but not all? Maybe some scientists within a lab could get the information, not others. How would you run that sort of thing? Conditions of controlled access made us liable to security concerns. Although Export Administration regulations and ITAR, the International Traffic in Arms Regulations, can restrict certain kinds of transfers, export controls were not seen as a good way to communicate public health results. So in the WHO consensus statement, they very clearly said that redaction with a mechanism for providing restricted information to legitimate recipients is not currently a viable option. And the lesson that I would give you is on the role of scientific publications, that publishers serve a vital role in sharing peer-reviewed information, and we need to be free to do that. Redaction is not a good strategy. It does not serve the scientific community. No system has been found to provide controlled access that would serve both health and security interests. Each time we thought we were taking a step closer to untangling this mess, it seemed to get more complicated. And I couldn't resist. At times we sympathized with the words of the revered philosopher, Groucho Marx, who said, "Politics is the art of looking for trouble, finding it everywhere, diagnosing it incorrectly, and applying the wrong remedies." To give you a flavor of the complications as we saw it, and you know the history, after further deliberation, the NSABB decided the papers could be published in full, although they needed to be edited further and re-reviewed for clarity. However, Ron Fouché, whose lab is in the Netherlands government decided that he needed an export license to publish the paper or even post it on the lab's website so it could be accessible to readers outside the Netherlands. The government based their decision on a 2009 European Union regulation and a corresponding Dutch law banning the export of goods and technologies that have dual-use potential. The regulation does have an exemption for basic science research, which they defined as an experimental or theoretical work undertaken principally to acquire new knowledge of the fundamental principles of phenomena or observable facts, not primarily directed toward a specific practical aim or objective. Basic research. Well, Fouché said his study fell in that category because he's interested in a fundamental question. What makes flu viruses transmissible between mammals? Moreover, he said the government had never done such a thing before. It was unprecedented. However, and in this picture you see Marion Donker, who is the head of the Public Health Department at the Ministry of Health, Welfare, and Sport. She pointed out that Fouché himself had stressed the practical benefits that his findings might have, from helping prevent pandemics to testing drugs and vaccines against pandemic influenza. So she said it's not basic research, it's applied research. So all of our efforts to prove to the general public, to make the strongest possible case of how important this research was to humanity, had backfired. It opened the door to it being called applied research and coming under these rules. Now, Fouché threatened to publish anyway. The Dutch government casually reminded him that if he did so, it would be a prison sentence. And fortunately, they agreed to grant Fouché the license, and we went ahead with the publication. So it's now a year later, and there have been international discussions. There have been discussions at the WHO about ways to harmonize biosafety. There have been many articles in many journals. The US has issued rules on dual use, how to fund gain-of-function research. Does this solve the problem, at least for the journals? And the answer is no, not completely. There will always be surprises. There will always be pathogens not covered by current regulations or new uses for technology. What would we do, for example, if a paper came in that was not funded by a US agency, that had fulfilled all the requirements of the sponsoring country, but the reviewers said that it would have required further mitigation efforts in the United States? How much risk is going to be okay? There's no such thing as zero risk. What counts as significant as a public health benefit? Something unexpected always comes up in the course of doing the research. We have learned a great deal, and that does put us in a better position to deal with the next situation. However, we feel that, at least for now, we are still learning, and we're going to continue to have to be deciding these issues on a case-by-case basis, evaluating risks and benefits, evaluating our responsibilities and our liabilities. One question which has caused some soul-searching is that whether in this very impact factor obsessed world, does the fact that Science and Nature publish these sorts of papers drive more labs to work in this area than are justified given the safety concerns? I don't have an easy answer for you on that. Maybe something that we will raise in the discussion. And it is certainly something that we will consider, and it's something that will always drive us to control the hype and the publicity about these things to keep them reality-based. However, our bottom line is that this is vital research. And to help protect humanity, we need to encourage our best young scientists to be studying pathogenesis. And it is in everyone's interest, despite the obstacles, for this information to be shared. So with that, I thank you very much.
That was really, really interesting. And of course, you know that Groucho's involvement with avian influenza or bird flu was a lot deeper than a lot of people recognize, because one of his favorite questions was always, why a duck? So he may have had more prescience about this than we thought. So we're running ahead of time. I'm going to make sure that we'll be able to do the coffee break after Mike's presentation, and then we'll come back for the final two talks. Mike Imperial is going to talk next. And then we're scheduled to have a break, and then we'll come back for the final two presentations. And then we'll have, looks like, ample time for questions. I mean, this has been an absolutely terrific session. And I mean, it's each one of you that talks, you know, there's another maelstrom which is coming out of it, and all from different points of view. So it's really, really interesting. So the next speaker, maybe I gave the most unenviable job of all, was Mike Imperial from the University of Michigan, and he's going to try to summarize at least I think he's going to try to summarize the NSABB perspective on this issue. So Mike?
Okay, thanks very much, Marshall, and thank you for inviting me to talk. So as Marshall said, what I'm going to try to do this morning is to summarize the NSABB deliberations on this topic. I will try very hard to make it clear when I'm telling you what happened with the NSABB and my own opinions, and you'll see at the end of the talk I am going to take the opportunity to give you my own opinions, because if I couldn't give you my own opinions, you might as well have just had someone from NIH come up here and talk about the NSABB. So hopefully you'll indulge me a little bit at the end of the talk. So what I'm going to do is take you through the history of NSABB and then talk about the lessons learned. And then I'd also like to pose some questions at the end that I think dovetail with some of the things that we've already heard about. So just as a reminder, NSABB is the National Science Advisory Board for Biosecurity. Arturo mentioned it already today, and he already talked about what our charge is, which is to advise the U.S. government about the risks and benefits of so-called dual-use research. And the NSABB was born out of the Fink report that Arturo showed you a picture of earlier on during his talk. And we've been deliberating on dual use since the summer of 2005. In fact, our first meeting was the same day that the botulinum toxin paper came out in PNAS. So it was a very special day in dual use history, I would argue. Okay, so skipping ahead now to the fall of 2011. So the U.S. government asked us to have a look at these two manuscripts, one from Ron Fouchier that was submitted to Science, and then the other from Yoshi Kawaoka's lab at the University of Wisconsin that was submitted to Nature, that dealt with high-path H5N1 influenza and attempts to understand whether or not these viruses could be made more transmissible. And I have to point out, this is not the first time that we were asked to review manuscripts. We were also asked to review the publication of the reconstruction of the 1918 influenza virus back in 2006, I guess that was, maybe, Jeff? 5, sorry. Okay, so our approach whenever we tackle a problem at NSABB is to convene a smaller working group to make some initial delving into the process and try to come up with some ideas. And so we put together a working group to assess the implications of the manuscript, consider the risks and benefits of communicating the results, and then provide those findings and recommendations to the full board for further discussion. And so in this case, the working group consisted of a subset of NSABB members, voting members. We also had ex officio members of the U.S. government who were also on the NSABB, and we also enlisted two outside subject matters, one who's an expert in influenza and the other is an expert in public health. And so we tried to have as much possible expertise on the working group to start with to get us going. So the working group worked very hard, a number of very long teleconferences, hours and hours of discussion. It engaged in questions and answers with both of the corresponding authors. And it used this NSABB communication tool as a framework for the risk-benefit analysis. I'm not going to show you the details of the tool, but it basically takes you through sort of a flow chart of a way to address these types of issues. And this was the product of another different working group early on that then presented it to the board and was accepted by the board. And if you'd like to find the communication tool or any other NSABB documents, they're present at the website on the bottom of this slide. So you can find it. And I found that if you don't type the www here, you don't get to the website. So you can't just type biosecurityboard.gov. I don't know what that's, probably some government restriction there or something like that. In any case, the working group came up with some recommendations and findings, presented that to the full board. The board discussed those in a number of teleconferences. All of these discussions were closed because, remember, these were manuscripts that had been submitted for publication and therefore were still confidential. And therefore, whereas NSABB normally is an open body, in this case, we had closed deliberations. And so we issued our findings and recommendations to the U.S. government. And I would just like to point out that, so I'm a virologist. I don't study influenza, but I am a virologist. I have never read two papers as many times outside my field as I read these two papers, just because of the importance of this topic and really trying to understand what was going on there. So, again, after hours and hours of deliberations, at the end of November, and I remember this was just before Thanksgiving, we had our final teleconference and came up with our findings and recommendations. So what are those findings? Number one, we noted that this was really important research. So there are a couple of things here. Number one, it was very important to know whether these viruses could become transmissible between mammals. And this is something that was debated in the influenza field itself. And in fact, there were many very outspoken leaders in that field who said this will never happen. And so I think it was very important that these experiments could be done and to show that this can happen. And number two, the way or the mutations by which one can attain this phenotype were important to know because it gave us some information as to what we might want to look out for. And so from the public health point of view, it also seemed that this was an important piece of information to know. But of course there were concerns, and you've heard about some of the concerns, and at that time it was mostly about the potential misuse of the specific information. So could someone who wanted to do harm take this information and basically reproduce the results without having to go through ferrets, just take those mutations, build a virus, and use it to cause harm? And Barbara's already gone through some of the potential actors, if you will, who might be able to or willing to do that, and those are certainly things that fed into our discussion, although as Barbara said, it's really hard to know exactly who might want to do harm. And so our recommendation was that, as you've heard, the conclusions of the manuscript be published without the experimental detail or the exact mutations. And so this was unprecedented for a number of reasons. Number one is the history of scientific publishing in the life sciences. So we depend upon open communication of our results in order to further the field. So that's a given. It's something that was sort of immutable at that time. And number two, as Arturo, I think, alluded to in his talk, on NSABB, we had spent many, many hours trying to think of things that we would not want to see published, legitimate research. Remember, dual use is legitimate research that could be misapplied, and we never, ever came to the type of consensus that we did on these two papers with respect to saying, whoa, wait a minute, there's something here that we really need to stop and think about. So it's unprecedented on both those levels. And I have to also remind you that we completely understood the ramifications of making a recommendation like this with respect to the impact that it could potentially have on the scientific enterprise. And so we did not take these recommendations lightly. Now, as Barbara alluded to, we also recommended the addition of language that would really show the public that, number one, the work was being done carefully, number two, the importance of the work was made clear, and so to just reassure the public that this work was being done in an appropriate manner and that this wasn't just a bunch of crazy scientists in their laboratory trying to do something that might potentially cause harm. Okay, so we conveyed those recommendations to the NIH. The NIH conveyed those recommendations to the journals, and Barbara just took you through what happened there, right, which was that the journals really wanted the government to come up with a way to share the information that was being redacted from those papers as a condition of publishing the redacted versions of the paper. Okay, and the feasibility of that type of mechanism was explored by the US government. Now, in the meantime, there are other things going on. You've already seen these. There was the voluntary pause on research that was signed onto by most members of the influenza community. The WHO had a meeting that you already heard about to talk about this issue with members of the influenza research community and also public health experts. And at the same time, the authors were clarifying some earlier comments that they had made. And in particular, Ron Fouchier was now trying to back off of some of the comments he had made, one of which Barbara showed you, saying this is the most dangerous virus you can make. And so obviously that didn't help in the long run. And not on this slide, and the other thing I want to mention here, because it already came up, is that at the same time there was a debate going on both in the press and in the journals about what the true mortality rate of high-path H5N1 is. And so this was all sort of going on in the background after the original papers were reviewed, and then as the US government was trying to figure out a way to comply with what the journals were asking for. And so the authors ended up submitting revised manuscripts. They incorporated additional data. In particular, the Fouchier manuscript incorporated, made a more accurate representation of its findings, and in particular, this issue of whether or not the transmissible virus, when spread by airborne transmission, was lethal in the ferrets or not. And so the US government asked us to come back together and review these new manuscripts, and this was our charge. So taking into account the additional information, epidemiological information that would be presented when we met, and also security information that would be presented at a classified briefing during that meeting, we were asked again to assess the dual-use implications, consider the risks and benefits of communicating the results, and develop findings and recommendations. And I want to point out something important here, because this is a misconception that's been out there, is that we were not asked to reconsider our original recommendations. We were asked to deliberate on these new manuscripts, taking into account all the information that was put together in the interim. And so this was a new recommendation. It was not a revised recommendation, even though these were revised manuscripts. And so we met in Bethesda, and we heard a number of things. So we were able to read the revised manuscripts, although we had to sign an export control license to be able to access those manuscripts. We heard from the NIH on the what they had found out about potential controlled sharing of the information, and it was not good. And Barbara mentioned some of the reasons why this was turning out to be less than feasible. We heard briefings from the WHO meeting and also from this ASM BioDefense meeting last year. We heard perspectives from the two governments, the Dutch government and the Japanese government, because Yoshi Kawaoka also has a lab in Japan, and so they were also involved in these discussions. We heard presentations from both Yoshi and Ron, presentations by other experts in the field. And we also did receive a classified threat briefing that we brought into our deliberations. And so we talked about this with the authors, the other experts. We did have a closed deliberative session at that point. And by closed, what I mean, it was just the NSAB members and not all of the other people who were asked to attend that meeting. And then we drafted our findings and recommendations. Okay, and I just want to remind people here of another thing, and that is that the expertise that was brought to this discussion is broad. So a lot of people out there think, well, you know, NSABB is a bunch of biosecurity wonks, and we really don't understand the science. But that's not the case. So many of us on the board are active working scientists. We study various different pathogens, and so we have a good sense of what's going on with respect to the biology of the system here. And also we did bring in a number of different influenza experts to help us with our discussions. Okay. On the other hand, yes, we do have security expertise on the NSABB, and we did have the classified briefing that I mentioned earlier. And so the other thing I should point out is that NSABB also has a couple of members of the public, and so we did have a public perspective in terms of these deliberations. So let me tell you about the recommendations, and then I'll tell you about the findings behind those recommendations. So as you know, we recommended unanimously that the Kawaoka paper be published in full. And then we also had a split vote on the Fouchier paper. So by a 12-6 vote, we recommended that this paper should be communicated, although we were still not happy with the way the paper was written. And part of the problem there relates back to this export control issue, because science was not able to send it out for peer review because the Dutch government had slapped this export control restriction on there. And so we were hoping that it would still undergo a round of peer review to clarify some of the things in the paper. And then we also recommended that the U.S. government needed to keep working on this, to develop national and participate in the discussions internationally about the oversight of dual-use research of concern. Okay, so what were our findings? So the majority of NSABB came to the following conclusion. And by the majority, I don't want to imply that everyone agreed on every one of these particular topics, but these were the majority findings as the consensus. Number one was that the data were not immediately enabling. And so there was a discussion that it would actually take quite a bit of expertise to be able to reconstruct these viruses in order to cause harm. The second was that the data may benefit public health and surveillance efforts, and that was probably one of the biggest items of discussion during our deliberations. It was important to note that global cooperation was important, and so we heard from some of the international individuals who were there in the meeting that they really felt a need to have these data available in order to help their efforts in terms of surveillance, and we thought that we had to be careful from a political point of view in the U.S. as to whether we were going to be trying to dictate what the world really needs. We found that the work was done under appropriate biosafety conditions. Both labs used BSL-3 enhanced conditions. We also found that there was, as I said, an urgent need for the U.S. and international entities to develop policies for the oversight and communication of dual-use research of concern. And then finally, that there was a critical need for a mechanism for disseminating sensitive scientific information. And we were told at the meeting by some representatives of the U.S. government that despite the fact that at that particular point it didn't seem to be feasible, that there were still ongoing efforts to try to figure out a way to deal with these types of issues in the future. And so the minority view basically hinged on two things. Number one was that some people thought that the data in the Fouchier manuscript were immediately and directly enabling. And this comes back to the definition that Jeff put up on there. How do you read those words directly misapplied, et cetera, et cetera? And so there were some people who thought that these data really were able to be directly misapplied. And then, as I said, there was a big discussion about what the real public health utility of releasing these data would be. And there were a number of people on the board who felt that the public health infrastructure was just not robust enough to be able to take these data and really put them to good use in a reasonable time frame. And so this is why then we had the split vote. The other thing that the NIH and the U.S. government asked us to do was to come up with a potential framework for how we might look at these types of experiments in the future. And so Arturo actually led the working group that came up with this framework that was then adopted by the NSABB late last year to talk about how the government might decide about funding research for generating high-path H5N1 viruses that are transmissible. And so, again, you can see the framework. If you go to the website, it defines the scope and applicability. What types of experiments does this refer to? What types of criteria should be met? The characteristics that might warrant additional review, and then underscores the importance of assessing and managing biosafety, biosecurity, and dual-use risk. And it's this framework that really made its way into the government policy that just came out last week. So the U.S. government has also received input from other places. So again, the global health implications really mean that there has to be broad input with respect to the framework. So as I said, NSABB discussed the framework as a full board at its last meeting. The RAC also provided recommendations on biosafety issues, and you probably know that the RAC has also recommended that these types of experiments be carried out at BSL-3 enhanced containment facilities. And then the government also put together a workshop that was held in December to talk about these issues and get a broader input into the way that the government should handle funding decisions about this type of research in the future. And so just to give you an update, at the March NSABB meeting, the government released its policy about how it was going to review this type of research, not just with respect to high-path influenza, but with respect to a number of different toxins and agents, the so-called Tier 1 agents that you're all aware of, and how to deal with that. The funding framework for H5N1 research did just get released last week, and you can find that at the U.S. government website. And then the government has also proposed a policy for how institutions should oversee dual-use research and is looking for public comment, and that was just published in the Federal Register last week, and so you can go and comment on that if you're interested in that particular topic. And then finally, I finally get to say something that no one else has talked about. There is a WHO meeting this week to talk about the broader issue of dual-use research of concern, and again, trying to bring together people who bring a global perspective to this issue to see if they could come to some sort of consensus about how to move forward on this important issue. And so that's going to end my history, and now, as you can see, I've changed the background of my slides, so you'll know that now this is me talking and not me as member of the NSABB. So there are a number of lessons, and I've just listed a few here that I want to point out. First is that certainly going into this in the fall of 2011, there was still an acute lack of awareness of the DIRC issue. And this was in the scientific community, but more astoundingly, as Barbara mentioned, it appeared that the NIH got blindsided by this whole issue, which made no sense to me because here we were, NSABB, meeting on the NIH campus since 2005, discussing these issues, and yet somehow there was a disconnect and the NIH didn't seem to be aware. Because one of the things that NSABB had recommended early on was that projects had to be assessed for their dual-use potential right from the beginning. And yet somehow this was not happening, and so that was a little bit disturbing to me. The second is, obviously, how the results of DIRC should be communicated is a very, very subjective issue. People bring different insights, different experiences to these types of issues. And so that's something that we need to keep in mind, is that there are a lot of different, very informed opinions on this particular issue. And so for that reason, I think that the discussions about these issues have to be broad and they have to be deep. So this is not something that we can take lightly, especially as we're sort of in the infancy of this whole type of discussion. And I think that these types of discussions are going to be coming up more and more frequently as we move forward. We already heard about another paper that Jeff talked about. There are going to be other papers coming through, and so we have to figure out a way to get the appropriate people involved in these discussions in order to reach a good consensus that's going to allow us to move the scientific enterprise forward while still protecting the public from any unneeded risks. I think it's also important to have disinterested parties involved. So, for example, I think if we're talking about high-path influenza, those decisions can't just be made by the influenza community, right? And that's where I think that the NSAB is really a useful group of people to use, because we do have that broad expertise. And obviously that we don't have all the expertise we need, and that's why we brought in some of the other expertise as we moved forward. But we can't just rely on the authors, or we can't just rely on the funding agency in order to have these discussions. They really have to be much, much broader than that, and it has to be people who don't have a vested stake, although to some degree, since we're all members of the scientific community and all members of the public, we all do have a stake in these issues. I think that authors and journals need to work to avoid sensationalism, and so you saw the comments that Ron Fouchier made. I think that to some degree the high-impact journals bring this on themselves, because authors have to try to sell their results to make it sexy so that these journals like Science and Nature will publish those data. And so I think the journals also have some responsibility here to be a little bit more careful about what they really expect from authors, and make sure that the authors' data really support their conclusions, and that the questions that are being addressed are really as important as the authors say. And then finally, another lesson here, I think, is that refusing to acknowledge that there are any risks is not a good strategy. And here, and I really hate to single out Ron Fouchier, because I think he's a very wonderful scientist, but I think he really made a big mistake by refusing to even admit that there are any risks involved here, because I think what that does is it really puts the whole field in sort of an awkward position, where now they have to fight to say that they really are being thoughtful in terms of their research. And to some degree, it puts the greater scientific community in an awkward position. And so I think we have to, not have our heads in the sand and say, well, don't worry, we're working here to benefit mankind, or animal husbandry, or plant science, whatever it is, which we are. But I think when we are doing experiments of this type, we have to really be honest with ourselves and admit that there might be some risks, whether they be biosecurity or biosafety or both. Otherwise, we're really doing a disservice to the field and to the public. And so let me just leave you with a few questions. Maybe I could provoke some discussion with some of these questions. The first is, how do we review manuscripts or projects for DIRC issues in an efficient manner? As you saw, this was a very long, drawn-out process, and it takes a lot of time, it takes a lot of effort on people. And is there a way to do this more efficiently? I would argue that if we really started monitoring projects right from the beginning, that it will become more efficient, because we won't have all this stuff that's kind of built up at the end of the process to deal with. But I think that's something we need to think about. Can we develop a more concrete risk-benefit analysis framework? So again, it's a very subjective type of discussion, but maybe there are certain things we could do to remove some of that subjectivity from the process. And that was something that we attempted with the framework that the government has now put out in terms of how it's going to review these specific experiments with H5N1 influenza. But remember, DIRC is a much bigger issue and doesn't just apply to that particular pathogen. It doesn't just apply to tier 1 agents. In theory, it could apply to any infectious agent, so we need to keep that in mind. How do we maintain a productive international dialogue? I think this is obviously going to be essential, because we could do all we want here in the U.S., but if other people are not going to play by the same rules, so to speak, then if anything, we may end up just shooting ourselves in the foot in terms of hurting the scientific progress that needs to be made. And then I think this is a discussion that we need to have, which is, are there experiments that should not be performed? So are there experiments where the benefits are either non-existent or potentially very low, but the risks are still very high? So is it okay to just say, I want to do this experiment because it's cool? It's a cool question to address. I think we need to think about this as life scientists as to whether this is a way to move forward. And then the last thing, and this is something I've been thinking a bit about, and I think it's something that we need to have a bigger discussion about, is this, and that is, do we need to reevaluate how life science research gets published? I don't know the answer to this question. I think that, as I said earlier, it's very important to us as scientists that we do maintain open communication. That's the way science works. We build on each other's research. We need to be able to reproduce people's results in order to really show that what they're saying is correct. But on the other hand, we live in a very different world than the world that we've been used to publishing open in. And I think that we need to have some sort of discussion as to whether there are other ways to communicate the results of experiments when they do pose certain types of risks. Again, I don't know what the answer to this. We may have this discussion and we may decide everything's fine the way it is now. Or we may decide that, yeah, maybe there are ways. And even though no one's come up with a good way to share redacted information to date, maybe we shouldn't use that as a reason to not keep thinking about it and come up with some means for addressing these types of things in the future. And so I am going to stop there. I gave you my history. I gave you my ideas. And thank you very much for your attention.
Thanks very much, Mike. Another slightly different perspective, but really, really interesting and informative one. So what we're going to do now is we're going to stop for about a 20-minute break. We'll come back. We have 2 more speakers, and then, I mean, this room is totally jam-packed. We'll have ample time for questions and at that point. So anyway, thanks for your attendance, and we'll see you all in about 20 minutes. And thanks to all the speakers. We're likely to have a few stragglers come in, but I think maybe we should go ahead and get started, and I think we'll have ample opportunity for questions at the end. And this has really been really interesting. I mean, it's kind of like the blind men feeling the elephant. I mean, they're all talking about the same thing, but each of the speakers so far and the two that are coming up, look at it from a slightly different perspective. Our next speaker is Vincent Munster, who I think he comes from the Netherlands, I'm not entirely sure. But he's going to talk about an aspect which I think is really important because, you know, ducks don't only live in labs and in zoos. I mean, they fly around the world from one place to another. And really understanding the biology behind the emergence of infectious diseases and pandemics really, I think, as more and more people appreciate, requires an understanding of the ecology in which the wild animals live and how their lifestyles and migrations may impact the emergence of new infectious diseases. So with that, I'm going to turn it over to Vincent, who's a tenure-track investigator at National Institute of Allergy and Infectious Diseases.
Thank you, Marshall, for this kind introduction, although he already knows me for quite some time, so I wouldn't him to do otherwise. So I'll be talking a little bit on ecology of avian influenza viruses and put a specific focus on the emergence of highly pathogenic avian influenza viruses. It's going to be a little bit redundancy in what Dr. Taubenberger already showed, but I think that's good. I think it's going to be very good for people to understand if we're talking about highly pathogenic avian influenza viruses, what they actually are. So I compiled a little bit more easier what they called in old time wheel of flu. Dr. Tauber showed a little bit more up-to-date one. But I think what's important to know that for avian influenza viruses, the wild bird reservoir harbors a myriad of all this great diversity of avian influenza viruses, subtype H1 to H16, Neuromyridae subtype aged N to 9. And then, of course, we have the new kid on the block, the H17 and the N10, who was recently discovered in bats, and we don't really know how these connect to each other. So if we think a little bit about this wheel of flu and how these viruses emerge and actually do this cross-species barrier transmission, we have basically two different mechanisms. Either direct transmission into a new reservoir, for instance, the recent outbreak of H3N8 in seals in Massachusetts, which caused an outbreak but is transient. So after the outbreak is gone, the virus is away and doesn't keep on circulating in this novel host. Or we have transmission into novel reservoir, for instance, horses, also an H3N8 viruses, but then keeps on circulating and forms stable lineages. Of course, that's what we've seen as well with the different pandemic in humans, H1, H2, H3 pandemics. We see a lot of circulation of first avian influenza and then swine lineage influenza viruses, a lot of crosstalk between humans and swine, and then, of course, part of my topic today is poultry and avian influenza which circulate in poultry. So, but then back to the basis, which is wild birds. And I've been studying wild birds for quite a while when I did my PhD thesis and after on when I moved on for my postdoc. And it gained a lot of attention with all these highly pathogenic avian influenza outbreaks. It dawned to a lot of people that we actually have very limited knowledge of what's going on in the wild birds, which are, of course, the main reservoir of these viruses. And I hope you can see it all, but we did a very large study over 10 years. We collected more than 50,000 samples, and what we came up was a picture that for most of the influenza A virus, the avian influenza A virus subtypes, we see them present in what we call the dabbling ducks. So these are mallets, teals, widgeons, very pretty ducks, feet upending in the water. We see a lower prevalence in geese. We see some prevalence in swans, not so much. Then we see gulls as well, waded species. beside all those species, we actually sampled a very large amount of species like passerines, where you look at robins. We didn't find any avian influenza virus in those species. Doesn't necessarily mean that they're not there. We just didn't detect them in these kind of studies. So we talked a little bit today about transmission studies, and I think these are transmission studies which are not that much put under scrutiny because we're actually trying to figure it out what's going on in the wild. But I think the basis of understanding avian influenza from a host perspective is also understanding avian influenza, what's going on in the wild birds. So classically, we thought it's a fecal-oral transmission route. Virus comes in, replicates in the intestinal tract, and then gets shot in the surface water, which, of course, this is a mallet feeding, upending in the water, make a very efficient transmission route. However, we started collecting a lot of different samples, both cloacal and oropharyngeal, and we actually see differences between different birds. For instance, these are white-fronted geese, and we actually see way lower prevalence in samples taken from the cloaca as opposed to samples from the oropharynx, suggesting that for these birds, actually more respiratory tract transmission, as for instance what would happen in the humans, seems to be more in place. Interesting thing is, and I'm going to show that in a later slide, is that we find most of the avian influenza subtypes in the mallet, H1 to H12. We only see a very limited amount of subtypes, predominantly H6 viruses, in these geese, suggesting that there's only not a change in host ecology facilitating the transmission of these viruses, but there's also a virus layer to it. So another step is, of course, understanding what defines a host. We did a lot of studies in mallets and dabbling ducks, and what we can see is that these viruses are prevalent year-round in these populations. They spike after the breeding seasons, where they have a big influx of new immunological naive young ducks. But if we look at other species, and for instance we're here looking at pink-footed geese, we started sampling them. This is the Netherlands, and this is really nicely tagged the migration of these species, and we sampled them on their way up to their breeding grounds, and each and every spot where it's green, they were negative for avian influenza viruses. However, we do in the red spot in Netherlands and Belgium, we see avian influenza viruses prevalent in those species. So we did a study where we looked at the seroprevalence, and here we see adults in March. So in March, they're on their way up to their breeding grounds. It is very high in the Arctic. So this is the tip of Norway. Arctic circle would be here. We see a very high prevalence in adults in March. But then if we look in July, July is after their breeding season, and they're actually trying to prepare themselves to move back for their winter migration to their wintering grounds in the Netherlands. We see prevalence is dropping, kind of suggesting that over here in their breeding grounds, they don't come in contact with avian influenza viruses, and that these avian influenza viruses don't circulate continuously in these species. We looked at juveniles as well, and juveniles in July completely negative, seronegative for avian influenza viruses. Whereas if we look in March, you see seroprevalence. So this again on the way up, we see seronegative seroprevalence building up. So the reason I'm showing that is because I think it's extremely cool and very interesting and very pretty bird species, but a host species can be a wide variety. So it can either be really contributing to the continuous circulation and the evolution of these avian influenza viruses, or it can only play a very limited marginal role in only part of the influenza A virus cycle. So in our surveillance, I already briefly touched upon that. We find all the different HA subtypes besides H14 and H15. We see in blue, which are all the viruses we isolated from mallets, so these are all virus isolates. And then in red, added to that are the viruses we isolated in different ducks, other duck species. So we see most of the viruses continuously present in the ducks, little bit. So here, the H6 virus is already mentioned in the geese, and then H13 and H16 almost circulating exclusively in the gull population. And I think for the remainder of my talk, specifically the H5 and the H7 subtypes are of interest. And if you lump those together, that in the natural population, almost 20% of the avian influenza viruses, these are all low pathogenic avian influenza viruses, are either of the H5 and the H7 subtype. So if we talk about low pathogenic avian influenza and highly pathogenic avian influenza virus, I think it's very good to know that this is actually based on phenotypes in poultry. So technically, this is a poultry disease. So a highly pathogenic avian influenza virus does not necessarily cause highly pathogenic phenotype in mammals. So based on this phenotype, we see either low pathogenic avian influenza viruses, which commonly circulate in all the wild bird reservoir, and they only have the ability to replicate either in the respiratory tract and in the intestinal tract. And if we look at the symptoms, they're very mild symptoms, and if you look at layer hands, you see a mild decrease in egg drop. And this basically encompasses all the different subtypes, H1 to H16. Then if we look at the highly pathogenic avian influenza viruses, there's something changing there. So it's not only able to replicate in the respiratory and intestinal tract, but it's able to replicate systemically throughout the whole chicken. And that's something we can see over here, kind of classic, what they call cyanosis, swelling of the combs, really bluish in the wattles as well, and it's very lethal. Normally these chickens succumb to disease within 24 hours. And that's what we call a highly pathogenic avian influenza, high mortality, but only the H5 and the H7 subtypes. So if we then look a little bit on the molecular level, and the molecular phenotype is based on the hemagglutinin, which is one of the surface proteins of avian influenza viruses, and it's used to attach and to enter the cell. It's based on one of the gene segments, and it's transcribed or translated as a so-called HO precursor protein, which needs to be cleaved to be active. And this is the cleavage site between HA1, which is the receptor binding site, and the HA2, which is the fusion site, and it's marked by this arginine. So interesting, if we look at the highly pathogenic avian influenza virus, we see introduction of a so-called multi-basic cleavage site. And basically this means that these viruses cannot only be cleaved by trypsin-like proteases, but more by furin proteases as well. And basically the trypsin-like proteases are only available in the respiratory or in the intestinal tract, whereas the furin-like proteases are systemically, hence the ability of these viruses to replicate systemically in poultry. So I've visualized this with a little experiment. So this is based on highly pathogenic avian influenza. This is the wild-type virus, and this is what we call the delta multi-basic cleavage site. So we actually took out from the wild-type highly pathogenic avian influenza virus, we took out that multi-basic cleavage site. So this is based on the plasmid. We transfected it, and then we either did it in combination with and without trypsin. So minus is without trypsin, and plus is with trypsin. So minus trypsin, we don't see any cleavage of the HA. And with trypsin, we see nice cleavage of the trypsin. The wild type, which has that multi-basic cleavage site, is nicely cleaved both in the presence and absence of trypsin. And we actually have it nicely shown over here, where we actually made those viruses by reverse genetics. And in black, we see the wild type H5 able to replicate to high titers both in the presence and absence of trypsin, whereas the delta multi-basic cleavage site is only able to replicate in the presence of trypsin. So basically, this is the basis of highly pathogenic avian influenza virus. So if we then look, so with all the novel tools and all the sequencing data available in GeneBank, you can actually nicely compile the classic basic cleavage site, which is present in wild birds. So I looked at a lot of these cleavage sites from isolates from wild birds, and they're always this QRETR, classic low pathogenic avian influenza cleavage site. Then if we look at different isolates from poultry, we see in over half, we see a saturation of these polybasic amino acids in the cleavage site, which either cause a direct phenotype change from low pathogenic avian influenza virus to highly pathogenic avian influenza, or it actually still stays a low pathogenic avian influenza virus. And what we actually think is going on over here is that this saturation of these polybasic amino acid on the nucleotide level inserts stretches of A's, which then causes pseudo-templated replication and adds another set of nucleotide aids in there, inserting those basic amino acids and then converting the low pathogenic avian influenza phenotype into a highly pathogenic avian influenza phenotype. But there's a lot of layers into the evolution which we don't really understand yet. So for instance, what the evolutionary benefit for this virus is, actually in this stage, we don't know. I think it has to do with the ability to infect birds or poultry in a lower infectious dose, so you would need less virus to cause stable transmission, but that's still quite hypothetical. So one of the highly pathogenic avian influenza virus outbreaks I was involved in was the highly pathogenic H7N7 outbreak in the Netherlands in 2003. So it's quite a big outbreak from the end of February 2003 till the end of May, 255 affected farms, in total 30 million chickens culled, 89 human cases, mostly conjunctivitis, one fatal case of acute respiratory distress syndrome, which was a veterinarian who visited the affected farm only once. If we look a little bit at a picture of the Netherlands, and this is a really nice composed picture. So in blue, we see wintering water birds in the Netherlands, and the bigger the blue dot, the more water birds we have. And I already showed the amount of avian influenza viruses circulating in those birds. We also see something nice more on an agricultural level is actually the density of poultry farms. And what's kind of specific is that in the Netherlands, 60% of poultry production was actually compiled on a very small area of around 30 square kilometers, which we see over here. So basically, all poultry in the Netherlands farmed was basically in this area, making it a really nice area if you have an outbreak to spark it completely out of control. So it's kind of classic that within my surveillance, we looked at all those low pathogenic avian influenza viruses, and for sure we found all these low pathogenic H7 precursor viruses directly linked to the highly pathogenic H7N7 outbreak and kind of closely related to other H7 outbreak previously in Europe. And then because of those new technologies, we were able to actually track the whole evolution of the virus from the first outbreak introduction, which is the virus over here, to the peak of the virus outbreak, first human case, and then end of the outbreak, and actually stop of the outbreak. So what we actually see is that from the first outbreak, and I've shown it below, there's actually a continuous evolution in poultry going on. So even though the virus evolves in a highly pathogenic variant, they actually see a lot of introduction of new amino acid substitutes all over the genome of this virus. And we actually looked into this a little bit more carefully, and of course this is the best known, the 627 mutation, which enables viruses to replicate very efficiently in mammalian species, which we isolated from the diseased veterinarian. All the other amino acid substitutions seem somehow to play a role into the ability of this virus to transmit from poultry to that veterinarian, suggesting that either continuous circulation in poultry and these mutations involved would actually predispose this virus to better replication in mammals. So a little chronology of the highly pathogenic avian influenza virus over the livestock. It's not completely up to date, but what I wanted to show is that there's actually a lot of change going on. And that's actually why I, on the top of my last slide with H7N7, I called it a kind of classic avian influenza outbreak. It was still kind of novel because we, again, had human cases, which for most of the outbreaks we don't. But the classic term is that these outbreaks are curtailed by mass culling. And all these outbreaks here have been stopped. So you basically have an introduction of a low pathogenic avian influenza virus in a poultry farm, causes a massive avian influenza, highly pathogenic avian influenza outbreak. Then you do mass culling and the outbreak stops. And I think that's what the things which actually completely changed with this high pathogenic avian influenza H5N1 outbreak, which is over here, that we see an introduction of the goose guangdong in 96, which suggests that it was already circulating before the initial outbreak in Hong Kong, 97, stamping out of that outbreak in 97, but resurfacing after 2003. And that still continues to circulate, and I think that's something to be extremely worried about. So another slide would actually show the changes as well is if we look back in all the human cases of avian influenza viruses, and starting on top with mostly H7 viruses, it actually hardly causes any serious disease. So we see a lot of conjunctivitis. H9N2 caused a little bit of influenza-like illness, but only here, for the first time in the 97 outbreak, that virus was able to not only cross the species barrier, which has shown for these viruses as well, but actually cause significant disease and mortality. So I think that's a big change as well for all these more or less classic introduction. The H5N1 still ongoing outbreak is very worrying. So that's why I call it a new highly pathogenic avian influenza outbreak, because this really adds a lot of novelty to what we previously know of these highly pathogenic avian influenza outbreaks. Starting the first outbreak in Hong Kong in 1997, that outbreak was curtailed and all the chickens were slaughtered, there was a lot of implements, but that virus resurfaced in 2003 and then spread all over Southeast Asia. Then in 2005, actually another novelty happened. We saw a spillback from this highly pathogenic H5N1 into the wild bird population, and it actually was able to spread extensively over very large geographical areas. So the first 2005 outbreaks were in Qinghai Lake and in Mongolia, and you see a very large westward spread deep into Europe, big outbreaks in swans in Rügen in Germany, dying swans in Britain as well, and then we actually see the virus spreading over a very large part of the world. So if we then go back a little bit to what I previously told you about what we normally see as hosts for avian influenza, low pathogenic avian influenza viruses in the wild bird reservoir, it kind of looks similar, but it's off. So what we see, so these are all the highly pathogenic avian influenza viruses isolated from dead and dying birds during a large-scale surveillance after 2005. It kind of looks the same, where we see a lot of involvement of ducks and swans, but are actually different ducks. These are actually the diving ducks than the ducks we normally see avian influenza viruses in. And we see a lot of additional species where we actually hardly ever see avian influenza virus in, for instance, bird of prey, which kind of makes sense because they would prey on infected birds and hence become infected. So there are a lot of changes into the ecology of this highly pathogenic avian influenza one if you would compare it to the normal low pathogenic avian influenza virus. So looking a little bit at evolution, which we can actually do in two ways. And the most easy way is actually looking just at the evolution of the HA, the H5 hemagglutinin, starting from 1969 Goose Guangdong, really moving into all these different lineages, and all different lineages are associated with different geographical regions. But of course, from a vaccine point of view, these different variants probably have a different antigenicity, and that would be so that's a big problem. But more interesting, if you look in this kind of similar slides as Dr. Taubenberger showed, for instance, with swine influenza virus, that's only a very small part of what we think is going on with these viruses. And this is from Guan Yi from Malik Pierce Group in Hong Kong, where they did very long-term surveillance of their avian influenza in their poultry. And you don't only have like the H5N1s, but they have the H9N2s, the H6N1s, and another lineage of H9N2. And there's continuous reassortment going on between all these different H5N1 over time with all these different co-circulating avian influenza strains in poultry. And we don't really know what that means in the long term, whether these viruses would be able to cross a species barrier more efficiently. I don't think we have a really clear idea. So I think, just to summarize it a little bit, I think we really have too little information on a lot of different levels. Ecology of highly pathogenic avian influenza virus, basically from a host perspective to a virus perspective. You can talk about transmission in birds, but also transmissions in mammalian species. I don't think we're not even close to scratching the surface. And I think we really need that information to be able to handle this outbreak, because it's really a big problem. We don't really have a clear idea of the drivers of the evolution of highly pathogenic avian influenza viruses. And of course the endemicity, so where do these viruses are right now? What is exactly the role in the spread of these highly pathogenic and avian influenza viruses? What is exactly the role of wild birds in that spread? So I thought I'd put this up a little bit as a teaser. It's actually my first presence at a bioterrorism kind of meeting. And I think this has been voiced quite a lot. Nature is the biggest bioterrorist. And I kind of hope to have shown you a couple of examples that it's actually all the man-made changes in the ecosystem, in the way we keep our large-scale animal husbandry, actually facilitated this highly pathogenic avian influenza virus to become the problem as it now is. So I think this is kind of a shallow remark. So that's my take on it. Thank you.
Well, thank you, Vincent. I think that certainly the world is our laboratory, I guess you could say, point of view on this. We have one more speaker, Nancy Cox from CDC, and we've heard a lot about ducks and viruses and people and things like this, but ultimately this issue boils down to human health. And what role does the kind of research and the topics we've been talking about today, what role do they play in our efforts to try to track influenza? And I think that's what Nancy's going to tell us about today.
So thanks, Marshall, for that introduction, and thanks to the organizers for giving me this opportunity to come and present today. So I'm going to try to discuss the implications of the research that we've been talking about for influenza surveillance. And I'd really like to start by pointing out that at CDC, I work at the nexus between surveillance, risk assessment, and risk response. And we are involved with a number of collaborators from around the globe, in addition to the World Health Organization, FAO, OIE, the animal health organizations. And we have the responsibility to take all of the information that we get from surveillance, interpret it, make an assessment, and help policymakers decide what to do. I probably haven't been able to sort of knit all of these, all of this fabric together very effectively in the time allowed, but I'll do the best I can. So As it has already been alluded to, seasonal influenza, which of course occurs after a pandemic virus has been introduced into the human population, has a huge economic and health impact. And I won't dwell on that, nor will I dwell on the impact of past pandemics. I would like to point out, however, that highly pathogenic avian influenza has already caused the death of hundreds of millions of poultry and wild birds. So it's been rather devastating, both for the bird population as well as for the protein source that's depended on by humans in many of these countries that are still affected. As has already been mentioned, there have been over 620 confirmed cases and over 350 deaths reported to WHO. And of course, this is caveated by these are the detected and reported cases, and there's probably a lot below those numbers. And then I'd like you to focus on an estimate by the World Bank, which has suggested that the costs would be about $3 trillion for a severe pandemic, such as one that might occur if H5N1 were to emerge. Now, here I'd just like to point out that in the surveillance realm, we are always challenged. We have all of these seasonal viruses, the B. Victoria lineage viruses, the B. Yamagata lineage viruses, the circulating H3 viruses that caused a lot of morbidity and mortality, particularly in seniors in the United States, the H1N1 pandemic viruses that emerged in 2009 and continue to circulate, and then we have all these viruses, which we call potential pandemic viruses, and we absolutely have to keep up with those viruses on an ongoing basis. And at CDC, we participate very actively in WHO's Global Influenza Surveillance and Response System, or GISRIS. And the GISRIS labs did indeed detect the first human cases of high path H5 infection in humans in Hong Kong in '97. We were very involved in working with the Hong Kong government at that time to look at what had happened and what might be done. And then in 2009, the GISRIS network was able to provide almost real-time tracking of the viruses that moved from country to country. And a lot of countries in Africa that had not previously been able to detect influenza were able to during the pandemic because of capacity building exercises that had taken place and funding that had occurred. And since 2009, over 3 million seasonal influenza specimens have been tested and reported by the national influenza centers that are part of GISRIS, and a lot of H5N1 data has also been analyzed. This slide just shows where the national influenza centers are in the blue triangles, where the WHO collaborating centers are located in these symbols, and there are H5N1 reference laboratories as well. So it's really a good network, and there are some gaps, particularly in Africa, but there are a lot of efforts to fill those gaps. So what are some of the recent activities? Well, I just got back from Geneva on Saturday, where there was a WHO consultation that was held where we reviewed data from all of these parties that I've talked about, the 140 national influenza centers, the WHO collaborating centers, and H5 reference laboratories. We analyze the data at the meeting, we make recommendations, and we write up those recommendations all in the space of 3 days. So we have to go very well prepared. Now, I had the privilege of co-chairing the meeting that occurred last week, and we have a wide variety of participants. A wide variety of participants. As you can see, there were 9 advisors and 18 observers. And we did have great participation from the veterinary sector with representatives from off-flu. So just review some of the data that we went over so that you understand that this is a very active network. It's not a passive network. We don't just sit back and wait for things to happen. We're constantly pulling data out of GenBank. We're constantly polling our collaborators to find out if they have any new viruses, any new sequence data, any new information to share. What is the risk assessment that's taken place in country? Can we do anything to help? So we reviewed data that have been accumulated since September, because September was the last time we met, and we had heard about outbreaks where there had been poultry outbreaks or where there had been human cases, and we reviewed the genetic information and the antigenic information. So we're looking at hemagglutinating inhibition assay results, so we can look for antigenic change. And so we really didn't have a lot that was unknown. We had heard what this clade of the latest human case in Indonesia was, but there hadn't been an official report, but there were no other gaps. And then we looked at the human cases that had been reported since that time. And the greatest number of human cases, as you will probably know, have occurred in Cambodia. And those have occurred really since the very beginning of 2013. And we have very good data on those cases already. Even though the data may not be in GenBank, the data are shared by the labs in Cambodia so that we can actually look at the sequence data and know where these viruses fall. You also probably know that there were 2 cases in China that clustered around the Chinese New Year, and we have data on those cases. This is an evolutionary tree just to show you that the Cambodia cases, the HAs of the viruses from the Cambodia cases fall into clade 1.1. So we know, and we've looked at the sequence in detail. We've looked for markers of receptor binding and other markers. And for the cases in China, we know that these viruses from those 2 cases fall into clade 2342. We have rather arcane a way of naming these viruses, but it means something to us. And that these 2 viruses from the 2013 cases were similar to a virus from a 2010 case in the same province. Furthermore, we had antigenic data, and for some of you this will look a little indecipherable, but I hope you'll be able to see that there is a homologous titer for the Anhui vaccine candidate virus, and so the homologous titer is 80, and these viruses from Guizhou province do not react well with the ferret antiserum made against that virus, indicating there's antigenic drift. There's another reference virus that shows essentially the same thing. And so, as a result, and I don't expect you to be able to see this, but these are all of the H5N1 candidate vaccine viruses that have been produced by the network, and they're in a vaccine candidate library. The majority of these have been excluded from select agent rule. Some of these have been chosen to be used in making pilot lots for clinical trials. Others have been used to make stockpiles for various countries around the world, including the U.S. At this last consultation meeting, we decided that we should make an additional vaccine candidate virus from the Guizhou human case because there was reduced reactivity with the current vaccine candidates. So it's a very, very active type of network, and we're constantly doing risk assessment, and then our actions are guided by that risk assessment, and we make candidate vaccine viruses and then interact in the U.S. with colleagues within the government, including colleagues from BARDA, and our information is used for decision making. So I just wanted to spend a couple of minutes talking about the very significant challenges that we have in doing surveillance and in keeping our attention on H5N1 viruses. I believe that, you know, the world is not a simple place, and one really has to look at the context in which these outbreaks or these cases are actually occurring. And they're occurring in a world that is increasingly crowded, increasingly connected, and increasingly convergent. And I'll talk just a little bit about what I mean and how this impacts influenza. So I'll focus a bit with our population challenges just in terms of human, bird, and pig populations around the world, because these the convergence is really where people, pigs, and birds come together, because these are the major sources of influenza. So there has been really a phenomenal growth in the human population, and so 11 billion people are expected to reside on the earth by 2050. More importantly, I think, is that over 80% of this population increase has occurred in developing countries. And so by 2050, greater than 80% of our population will be projected to live in Asia and Africa. And those are areas where we don't have wonderful surveillance. It's improved a lot. There have been marvelous investments, but there's a lot of more that could be done. And there has been very substantial growth in cities with over 10 million inhabitants, and these are called megacities. And in these megacities reside younger and poorer populations, making them particularly susceptible to outbreaks of diseases, including respiratory diseases. Right now, there are 23 megacities, and they include the cities I've listed here and additional ones. And these poorer megacities face healthcare, public health infrastructure, air pollution, and they also have stressed agricultural supply chains. So consider Bangladesh and consider Dhaka. In 2010, Bangladesh had a population half the size of the United States, living in a country the size of the state of my birth state, Iowa. In 1970, Dhaka, the capital, had a population of 1.4 million, which expanded 11-fold to 15.4 million in 2011. And the number is expected to reach 23 million by 2025. That is pretty staggering. In the Dhaka slum of Kamalapur, population density reached over 100,000 population per square kilometer. And 44% of that population is under the age of 20. It's been determined through surveillance supported by us and many other groups that seasonal influenza is identified as an important cause of illness and death. And as a result, multiple groups, including the CDC, is now conducting surveillance in live bird markets in Dhaka with near real-time sequence information now available to us. So the consequences of living in an increasingly crowded world is that we need more meat. We wouldn't have to have more meat, but meat is more popular as a protein source. And so there's been a 150% global increase in this demand between the mid-1960s, sorry for the typo, and mid-1990s. For reasons that are obvious, I think, increases in farming poultry and pigs are the greatest. And so there's been an increase in poultry production from 4.3 billion in the early 1960s to 21.5 billion in 2010. And there's been an increase in the pig population to 1 billion pigs living on the earth at any point in time, and some of those are going to market, and so it's a very dynamic situation. So as this demand for meat in these megacities I've already mentioned continues to increase, the infrastructure and biosecurity for safe food should increase proportionately, but unfortunately it's really lagged behind. So now let's look at Jakarta, Indonesia. This is another place of great interest when we're talking about H5N1. It's a city of 10 million people where they consume 1 million birds a day. And in order to supply the live bird markets in the city, there are over 500 trucks from many locations on the islands of Java and Sumatra supplying birds to Jakarta, making multiple trips back and forth between the farms and the live bird markets. And I've got a picture of one of the live bird markets up there on the right, just to show you some of the conditions. The conditions in Jakarta are really not different from those in Dhaka and other growing cities. And so it's really tremendously challenging to limit the emergence and spread of avian influenza. But we have set up enhanced surveillance in East Jakarta to really look at whether there are a lot more H5N1 cases and maybe mild cases occurring there than have been detected. So where do we stand today? Animal health experts agree we're really decades away from eradicating H5N1 in poultry. But on the other hand, we have increasing ability to do high throughput Sanger sequencing and next generation sequencing in a number of locations around the world. And there has been, indeed, a huge increase in the available influenza genome sequence data for both seasonal viruses, but especially relevant for us today, for H5N1 viruses. But we know that the influenza sequence data alone do not allow us to assess the pandemic potential of a given virus and to do risk assessment and proper risk response. So Vincent was able to show you an evolutionary tree showing the great complexity of and diversity within the H5N1 HA genes that are of the viruses that are circulating in birds at the present time. So it's really critical for us to, as we're doing this surveillance and as we're doing risk assessment and determining how we're going to use our ever-increasingly precious resources, we really need to know what to look for in terms of changes in receptor binding, in host specificity, antigenic variation, ability to replicate in different species, ability to cause disease, sensitivity to our antiviral drugs, and of course, transmission in mammals. So the papers have been published, and in addition, in an effort sort of spearheaded out of CDC, we have put together the H5N1 genetic changes inventory and have published that online. I'm not sure, we published it online with very little fanfare, and I doubt that many of you know about this. But what we did was text mining as well as traditional searches of the literature to extract the relevant publications, and we had a lot of H5N1 publications. We had them read by 2 or more subject matter experts each, and then we listed all of the gain of function molecular changes by gene that conferred changes for host receptor specificity, for adaptation to mammals, for increased transmissibility in mammals, and for antiviral resistance. And so all of those changes are listed. And so this has been very, very helpful for us in terms of doing our own surveillance. We also then sent out the list this genetic changes inventory to collaborators around the world and had them determine whether we had missed significant publications or significant mutations. So what I would like to emphasize is that right now we are in the process, and I'm sure maybe other groups are also in the process, of writing bioinformatics programs which will automatically identify and flag molecular markers of interest in new and existing sequences. And so we'll be looking not just in a linear way at given mutations, we'll also be looking for combinations of mutations. For example, 2 changes in the hemagglutinin around the receptor binding pocket, and not just those mutations that have been already identified, but mutations that might similarly affect receptor binding and host specificity. And I mentioned we have an increasingly converging world, and we have a great convergence of information. And I think that there is just a tremendous amount that comes through. We hear about suspect H5N1 cases all the time, and some of us are suffering from flu fatigue and are just kind of tired of the whole H5N1 controversy. And so for some people, not much attention is really paid to these reports. But at CDC and at other institutions, we are constantly reaching out and trying to confirm what it is that we're hearing through ProMed, through scanning news publications, and so on. So information is instantaneous, abundant, and interlinked, and we mustn't forget this. We did a little experiment and typed influenza into a search engine, and there were 260 million results in under 0.2 of a second, and that's just how interconnected we are. So in conclusion, I'd like to leave you with a few thoughts. In this increasingly crowded and interconnected world, I think we have to think about all the tools that we have in hand. There are a lot of new technologies that we need to harness. There have been new regulations put in place, such as the international health regulations, that really do help us and do our job. And then, of course, we have some new agreements in place, such as the Pandemic Influenza Preparedness Framework, which was brought to agreement by the World Health Organization. Groups are constantly developing new tools and sharing them. So just as an example, at CDC, we spearheaded the development of the H5N1 clade designation tool so that researchers can just enter their sequence data into this tool, and the tool will tell them what clade that sequence belongs to. So I would like to conclude my talk by stating very emphatically that support for H5N1 surveillance activities must continue. I think it's obvious, but in this economic climate and with flu fatigue, I think it's questionable as to what level those activities will be able to be continued in the future. And finally, H5N1 research with appropriate biosafety and biosecurity conditions must continue so that we can better understand and respond to the ongoing pandemic threat of H5N1. Thank you.
Thanks, Nancy. That was also very, very interesting. I think if I was a duck, I'd probably want to stay away from Jakarta and Dhaka. I wouldn't want to fly over there. So what I'd like to do now is to ask all of the panelists to come up and take a seat here. 2, 4. We're going to need one more chair, Artur, so maybe you can grab one. And then I understand that there's someone with a microphone out in the one of the ASM staffers. Is that right, Judy? Judy's over there with a mic, so if you'd like to ask a question, if you can raise your hand, Judy will come around and try to call on you. So while everybody's getting seated and people are trying to formulate their questions, I'd like to ask one. Several of you talked about during the NSABB process about the need to actually evaluate the case fatality information about that virus. I wondered if you might clarify for someone, or multiple ones of you, might clarify for those of us in the audience maybe a little bit less familiar with that, why that information was considered so important.
I think the information was considered so important because you had a range up to 50-60% mortality, and the thought was that this was a very dangerous organism, and that those numbers were challenged. They were challenged in print. Then the print was counter-challenged, and currently I think that the case fatality ratio that we know of what happens in hospitals continues to be that high, but we don't really know what the percentage of out there, because the serology is not that good. Right, Nancy?
Anybody else want to comment on that, Nancy, or?
Yes, I think that there will be some publications coming out in the future that talk about some of the limitations of the seroprevalence data. But I think it's safe to say that although the case fatality ratio is likely to be, the calculated case fatality ratio is likely to be considerably higher than it is, we don't really know what it is. And I think that's the basis of some of the disagreements.
I see. Would you, the rest of you want to say anything about that, Mike, since you were sort of talking for the NSABB?
Well, I mean, I think Arturo pretty much covered it, but there was just a paper that came out a couple of weeks ago where another group sort of reviewed all the available data and came to the conclusion that the mortality rate is quite high, especially if one sticks to the WHO-defined serology cutoff.
I see. I see. Questions from the audience, I hope? Yes, sir, over here. Oh, if you can stand up, she'll bring you down now.
My question is, if a new pandemic H5N1 appears today, how quickly we can develop vaccines for that? Not the vaccines or the predicted virus which we have in store. It's a completely new pandemic virus.
Good luck.
Yeah. So as I understand your question, it is if a new H5N1 virus emerges, how quickly can we develop a vaccine? And so how quickly we can develop a vaccine is dependent on how distant the newly emerging virus is from those candidate vaccine viruses we have and from the viruses that are in the pre-pandemic vaccine stockpile. It's hard to predict. So it could take 4 months, it could take 6 months, it could, it is difficult to predict. I think that one of the encouraging things is that a couple of new influenza vaccines have been licensed in the United States, and they use different technologies. They aren't egg-based vaccines, and those vaccines could possibly be produced more quickly.
Thank you.
Somebody else over here. Paul?
So this is a question for Barbara. So has Science Magazine looked at the issue of liability? I mean, have you sought a legal opinion? If you would publish something and it would be used for a nefarious purpose, would you be open to litigation?
Certainly, we spend an inordinate amount of time talking to lawyers at various points in this process. That exact question, I don't have an answer for you on. It would depend very much on the circumstances. It is a question that our lawyers were concerned about. I think mostly we were concerned about our responsibilities and of wanting to be responsible to the global community. And that was our highest priority.
I think that's a great question, because if the NIH funded that research, would the government be liable if the ASM sponsored a conference where somebody presented data which suddenly turned into something like that? You know, would the conference organizers, for example, be liable for that? So, and if, you know, if all of these things were going on, I mean, you'd have to say, well, you know, who made the, you know, who really let the cat out of the bag? Was it the guy who spoke at the meeting in Malta? Was it Science Magazine who published it? Was it NSABB that redacted it or whatever?
There is another point I should
Yeah.
make. The information that was in the papers, the methods, that is, were all out in the published literature. It's not as if new methods were devised in these two papers. So we did go through the exercise of looking, by the time the papers were in review and we were considering publication, how much information had been spoken about, how much information could you find if you looked? And a lot of the information was already out there. Information about how many mutations, information about at least some of the regions where mutations had been found, all of the information about methods. We live in a different era now of instantaneous communication. So when you talk about liability, it becomes a very difficult question.
Michael?
So I'd just like to comment on that last point, because I don't want anybody to think that NSABB was deluding itself by thinking that by recommending redaction that someone couldn't go out and reproduce these results, because someone could have easily engineered the first couple of mutations, passaged things through ferrets, and gotten the same thing out the other end. And all along, we've known that you're never going to stop someone who's determined from doing something bad from doing it. But we thought that at the very least, we didn't want to give them the exact recipe in terms of the exact mutations that would be required, which would severely decrease the amount of time it would take to make such a virus. So we were certainly thinking about these things too as we undertook our discussions.
Okay, Arturo?
Yeah, I mean, I felt what was really important about that paper was that it happened.
Yeah.
Period. Not the mutations. The mutations, you know, I mean, listen, journals make us redact papers all the time. I mean, take us stuff out. Reviewers make us redact papers all the time. You know, this was very rapidly escalated to a much higher case. But one thing that I learned today that I'm happy about is that I heard Nancy saying that data is in fact being put into databases and may in fact become useful, because one of the major concerns was that here you had the important result is that the virus can acquire mammalian transmission. That's what I cared about. The other details I wasn't sure they were going to be used. And now I'm seeing that in fact there is a movement in that direction, and I think that's very good.
Yeah. Any
Can
other?
I just point out that journals we don't think of ourselves as redacting information.
Well, Barbara,
We take out information that the reviewers say is ill-founded.
But isn't
We
that
take it-
redaction?
No, because we were being asked to take out information that was very good information, so no one would use it. That's a very different kind of thing.
Barbara, they make me take good information out of my papers all the time.
Good. No.
That's why we need the NSABB. So I have one question I want to ask you guys. Several of you alluded to the fact that is work like this gonna work like this, and the biosafety and biosecurity considerations that are going to go along with it. Is it going to drive people to do this kind of work, or is it going to drive people away from it? And I think, you know, talking to a group of scientists here, I think that's something those of us who have to work with people who are working with select agents can sort of think that the constriction that which is being in, you know, like one of these pythons in Florida, you know, is having the effect of driving people away from some of this work, which in the end may turn out to be, totally important for global public health. And I know a couple of you sort of briefly mentioned it, but I wondered if the rest of you might like to comment on that too, like maybe you, Jeff. I know I can see you don't want to, but I'm going to have you as you do anyway.
I'm happy to comment. I don't know how to answer the question because there are pressures in both directions, of course, but I think that the very nature currently of working with pathogens that require high containment, especially select agents, is really complicated, and it requires an enormous amount of hoops to be jumped through. And I think that we do it and other people do it because we feel that there are important public health implications of that. But the question that was posed, and I forget by whom, as to whether if you wanted to do a postdoctoral fellowship, you would want to do it in a lab where experiments like this might not be able to be done or that they might not be able to be published. I think that you would have to seriously question that as a young scientist as to whether you would want to do that versus the large number of other important and interesting things that one could work on. So I think that it's important that this work be done. Of course, it needs to be done in a safe and secure environment with the kind of oversight we've discussed. But the very nature of this work is going to, I think, prevent or likely prevent young people from making a decision to go in that direction.
Arturo, what do you think?
I think that's an extremely serious problem. I think that, and I continue to repeat it, the best protection society, humanity has is the flu research community. Now we're going to put in all these regulations in place. We're going to make it really hard. If you had to do a PhD, right, where your work is going to get sent out and may get held up, you may need a year to get it to do it. Why do it in this area? So we have to be very, very careful because I think that to some degree society may be shooting itself in the foot. And people often don't get it. I mean, I can tell you that my lab works on basols and traces, and it is a lot, you look at the people in the lab, it's a lot harder to do some of these experiments than it is to do if you just go to another bench where people are working on different organisms that doesn't require select agent rules and things like that. So this, I think, is a major societal problem that needs a different type of discussion.
That's terrific. Anybody else have a question out there? Yes, sir, right over here.
I'd be interested in your opinion of what your interactions with the public are and what they think we are actually doing. We all scientists think about what we're doing is important and we think we should keep doing it, but are those public members on the board, what do they think? Are we a bunch of crazy hoo-has just running around?
So, the public members on NSABB fully understand the importance of a vigorous research enterprise and how important it is to move that forward. As Arturo said, our best protection against anything bad is knowing, as much as we can about these organisms. I can tell you that my interactions with just general members of the public over the course of this whole controversy have been that the public thinks that us scientists are crazy. Why are we studying this thing? Why are we making a virus that's going to be more dangerous? And it takes a lot of education to explain to the public why these experiments are important. And my personal view is, and even before we entered into this situation, has been that we scientists do a really lousy job educating the public, and that we have to step out and do that. I think one of the public members of NSABB calls us the white-coated priesthood, because we think that we know what's important and everybody else should just accept it for what it is. And I don't think that's the case. I think we have to do a much better job engaging the public.
Well, and I think that's a great way to end this symposium and a wonderful way to introduce tonight's keynote speaker on topic about teaching biodefense to Hollywood by Ian Lipkin. I'd like to thank all the panelists for doing an absolutely wonderful job, and look forward to seeing the rest of you around the meeting. Thanks again to everybody.